So we're now going to talk about reliability and considering whether or not an item or a group of items is reliable. And just as a reminder, reliability is simply whether we're going to get the same result or nearly the same result every time we apply the test. What reliability does not tell us is whether or not we're actually measuring what we think we're measuring. That's validity, and we need both honestly. But honestly also, I've used honestly twice here, in industrial organizational psychology, I almost said honestly again. Validity is less important. Validity is incredibly important in psychological science. If you say you're measuring emotional intelligence, you want to really make sure that it's a reliable, stable measure and that it's valid. It's measuring what you claim it's measuring. In most workplace settings, especially in practice, if it's reliable and it's related to an outcome you care about, it matters a little bit less whether you're actually capturing what you're thinking you're capturing. So for example, if we're talking about the theory of cognitive ability, we really want to spend a lot of time on determining, are we validly measuring truly what we consider to be cognitive ability? Have we captured all aspects of cognitive ability? If we're making this claim, can we back it up? Can we find that this measure of cognitive ability is highly related to any and all other measures of cognitive ability? If we're measuring cognitive ability specifically as it relates to your ability to perform as an engineer, and we have a test that is highly related to performance as an engineer, it matters a little less whether it's actually measuring truly cognitive ability or not. So I would actually say that within the practice of IO psychology, reliability and specifically the relationship to a predictor or actually to a criterion, an outcome that matters to the organization, often takes a little bit more of center stage. So reliability is the degree of consistency or stability of a measure. And there is a big hidden assumption here that what we're measuring is stable. So it's the extent to which a test score is free from measurement error, assuming we are measuring a stable construct. And reliability is trying to estimate how much of the true score is actually being captured by the measure. So whenever we're inferring the test score of someone, when we're actually looking at someone's test score, whether it is personality, cognitive ability, or love of Doritos, what we're getting is hopefully some form of their true actual score, something that we can only infer, plus or minus error. So that is also one of the big theoretical concepts, is that all measurement has some error. We are never capturing true score with a test score. Test score is always, at its best, the true score plus or minus at least some level of error. And examples of test error can be just about everything. It can be small variations in the test. It can be misunderstanding the questions. It can be changes in mood. So I'm generally an extroverted person, but depending on what's been going on, my mental state may vary that. So that stability, though it is a stable personality trait, does still fluctuate based on what's going on in my life. So that'd be another example of a test error. So for example, if my true score of extroversion on a 1 to 10 scale was a 7, but you measured me when I hadn't been around people much and I had just gotten back from a giant 3-day festival that I enjoyed immensely and I was really enjoying being around people, at that moment you might actually get an 8 or 9 from me. That would be my true score, 7, plus the positive error. Likewise, if you caught me after 2 weeks of grueling teaching and I just didn't want to be around people much anymore, I needed to recharge my battery, you might actually get a 4 or 5 out of me, which again is not my true score. This time it's minus error. So there's a lot of things that can cause error, and there's no way to completely get rid of error because we're humans. We vary. Things change. But if we actually are measuring a psychological construct that is likely to be successfully and reliably measured and also is related to workplace outcomes, it's probably going to be somewhat stable. So we're just accepting that there's going to be some error in that measurement. So when we're looking at reliability coefficients, almost always what we're doing is we're comparing the measure to some other measure that should be related to that measure. And usually what we're doing is correlations. We're usually looking again at interval or ratio data, and we're correlating the test with itself. We're correlating the front half of the test with the back half of the test. We're correlating the test with another test of a similar measure, or we're correlating the test with an actual criterion, an outcome, a performance. we're going to get an R, and that R is going to range between 0 to 1. Now, notice that I didn't say -1 through 0 to +1. Generally, we are looking for positive correlations. We usually want to frame things theoretically in the same direction. So we're rarely actually looking for negative correlations when we're looking for reliability. In fact, that would generally mean that we have some form of scale that we probably need to recode in a direction that makes more cognitive sense. If you actually have a strong negative relationship, that doesn't necessarily mean that it's not a reliable measure, but it also is going to be hard for practitioners and decision makers to make a lot of sense out of that. So again, generally the higher the reliability, the less the error. And so, for example, if we have a reliability coefficient of an R of 0.80, that means that the R squared, the effect size, is 0.8 times 0.8, which is 64%. So that means that 64% of what we're measuring is probably actually systematic variance. It's actually what we're after. It's effectively an estimate of true score, but 36% is not being explained by that. That's the error. So that's one of the ways we can estimate error. The higher the reliability, the less error there is. So there's four main methods of estimating reliability. There's test retest, equivalent forms, internal consistency, and there's multiple forms of that, and also inter-rater reliability. So we're going to talk about each in turn. Test retest basically simply means that we give someone the same test after a period of time. So we give them the test, and then we wait for a while, and we give them the test again. If what we're measuring is a fairly reliable trait, a reliable construct, we should see fairly similar scores across multiple people. In other words, if we give this test to 100 people, the people that scored very lowly the first time should probably score again at least somewhat lowly the second time. And the people that scored very high the first time should again probably score fairly high the next. Now their scores aren't going to be identical because there's going to be some error in there, and that's also going to give us that estimate. So we're going to get how much of this variance is systematic, probably estimating true score, and how much of it is error. Generally, as far as doing test retest, we want to think about how long we wait. Pretty much the rule of thumb is you should probably wait at least 2 weeks, but probably no more than 6 months. And the reason for this is that we do have changes in our psychological makeup. Our personality slowly shifts over time. So we're going to find greater differences the longer we wait. The reason to wait at least 2 weeks is to make sure that you're not actually getting a test retest effect where people are remembering their answers from the first test. We want to let it kind of fade a little bit into memory. Equivalent forms is basically when we have two tests that are identical but different items. And how we do this is usually item response theory. So we could have a test bank of hundreds of test items, and we'd create two tests with a very similar profile of how many difficult questions, how many moderate questions, how many easy questions, and how discriminatory are those items. So basically we'd use item response theory to get very similar items that are different in an equal number on both tests. We would give people both of those tests, and again, we would look for that reliability coefficient. How well did those two forms correlate with each other? Internal consistency is simply giving people the test one time and then using those scores to kind of split the data set up to look for this. Again, for the correlation. One thing we could do is split halves. We basically could divide the test in half, and that could be odds versus evens, that could be randomized, that could be the first half versus the second half. And again, as long as those items are all supposed to be measuring the same construct, we should find a fair amount of consistency, reliability between those two halves when we run the correlation. We can also do a Cronbach's coefficient alpha, and this is a technique that is often used. And basically what it does in the very broad sense is it compares every single item to all other items and then collapses all of that information into one single score. So a Cronbach's alpha will give you a fair amount of information. It will give you how reliable it is. And by the way, the rules of thumb for alpha is 0.7, 0.8, and 0.9. 0.7 or higher is usually a good enough Cronbach's alpha for at least experimental or research purposes. A 0.8 is usually considered a fairly solid alpha, but still got a fair amount of error. And if you're actually using a scale to make decisions about people, if you're using it for the purposes of diagnosis or hiring, firing, or promotion, you probably want to see an alpha of 0.9, representing that you're capturing mostly true score with this particular measure with not a whole lot of error. Cooter-Richardson 20, and there's also various forms of the Cooter-Richardson or KR test, are specifically designed to do the same thing Cronbach's alpha does, but with ordinal or categorical data. And finally, inter-rater reliability is when we don't necessarily have a series of items. What we have are individual raters making a determination. So we're going to actually find that inter-rater reliability analysis for measuring reliability is actually commonly going to be used, especially if we're looking at multiple managers interviewing and giving ratings to someone based on that interview. Again, if it's working correctly, it shouldn't necessarily matter which interviewer interviewed people. We should find consistency. So if one person is interviewed by 4 different people, they should give fairly reliable ratings to that same person, not necessarily error. Now, if we find the inter-rater reliability is low, someone gave the person a 5, someone else gave them a 2, and someone else gave them a 1, that's not very reliable. That means it completely depended who interviewed that person, whether or not they were rated high enough for the hire. So these are, again, what we're doing is looking at measures of reliability and how we can use them to test and to ask the questions of the various ways we're measuring psychological constructs for the purposes of prediction, promotion, determining who needs to be hired, who needs to be fired, who needs to be trained, who needs to be promoted. Are we using reliable measures of things that are related to, again, the criterion? So just briefly, test, retest reliability. The same group takes the test at 2 different times. And generally speaking, this is called the coefficient of stability. So if you ever see the words coefficient of stability, you know they did a test, retest, reliability test. And again, we already kind of touched on the time interval. We usually want to give enough time that people don't specifically remember the items of the test, but not enough time that a slowly changing personality or attitude or knowledge base was changed. Now, longer times are less important when you're looking at something that is known, again, past research and theory, to be stable over time. It becomes a bit more issue when you're actually testing people that are developing, so younger people, people that are currently learning skills, developing their personality, or people that are older and are maybe in the process of decline. So you want to take all of that into account when you're thinking about time interval. So generally speaking, if you were actually using a test, retest reliability with people fairly stable in their skill sets, already established in their jobs, and in their mid-30s, you could possibly wait much longer to do a test, retest. You could maybe take 6 months or even a year. If you were measuring reading ability in 7-year-olds, you probably need to take a test, retest fairly quickly. You can't wait a long time because you're going to find large differences between the test and the retest based on the development. And likewise, if you're dealing with, for example, a test of physical ability with people in their 70s and 80s, waiting 6 months or a year, you may start picking up just natural decline and not necessarily the stability of the trait you're trying to capture. Equivalent forms can also be called parallel or alternate forms. 2 different tests designed to measure the same thing are given to the same group. You probably are going to vary the order of administration. What that means is some people are going to get test 1 first and test 2 second. Other people may get test 2 first and test 1 second. And generally speaking, what we're looking at here is the coefficient of equivalency. Now, generally, you're going to use this technique when you actually need equivalent forms. You need multiple versions of the test. And some of the reasons you'd need equivalent test forms is, one, if it's a pen and paper test that a lot of people are going to be taking at once in an enclosed space, you may want to actually have multiple forms to where if someone does try to cheat and test and look at someone else's test, there's a good chance it's a different test. You may also want to do it if you're worried about versions of your test getting out, or also if you're creating an adaptive test. So an adaptive test means that the items you get may be completely different every time you take the test. It's randomized. And that is often done by companies that want to make sure that anyone taking the test can't find a copy of that exact test available online for them to, again, cheat with. So those are some of the reasons we might use equivalent forms. They're very popular in organized testing and companies that actually create tests for a living. They often will have tests that are basically drawing from a test bank of equivalent forms to where you're never necessarily getting the exact same test every time you take it. And again, this is for security and also just for rigor reasons to make sure the tests are harder for people to actually cheat on. So again, we talked about internal consistency reliability. Do people perform consistently throughout a single form of the same test? Higher the internal consistency tends to mean that the items hang together, they're reliable, they're at least some indication they're measuring a single construct. And again, we talked about the three types. There's split halves, where we basically use some method to split the number of items into two groups and run a correlation between those two groups. There's again the convex coefficient alpha, which compares each item to every other item in the test. And finally, the Kuder-Richardson formula 20 and KR20. There's also a KR5 and 10. And these are basically better forms for ordinal or categorical data. And often they are used actually in, again, kind of knowledge tests or multiple choice tests. So the split halves method, one test is administered one time, and then you split the test in half. Then you correlate the two halves. In general, longer tests will become more reliable. Now, there's a quick relationship formula here, and it's in your book as well. It's the Spearman-Brown prophecy formula. And basically what it allows you to do is to estimate what you would actually need to do, how many items you'd have to add to the test to get to a reliability you wanted. So for example, if you were going to actually figure out what is the corrected reliability, you would actually multiply 2 times the current reliability divided by 1 plus the uncorrected reliability. So what this allows you to do is actually create an estimate of what would be required to actually calculate a bigger test. So what this basically says is if I have 50 items and I currently have an uncorrelated or an uncorrected reliability of R of 0.80, but what I want is a correlated reliability of 0.89, this is a technique we can use. This isn't used very often. I mainly just presented it here. Take a look at the textbook if you're a little more interested in this. It's another way, though, that we can use some of these techniques and psychometrics to kind of make our job easier. So what this would be actually best used for is that if you had a test bank of hundreds of items, you created a 50-item test, you did a split half method and found you had basically a coefficient of reliability of 0.80, but you were wanting 0.9. You could use this formula to figure out how many more items do you need to add to actually get up to that. Because here's another thing, the more items you have, generally the more reliable the test. It's just a natural process that as you ask more and more items that are asking kind of the same thing, the more reliable those items become in general, assuming they're all decent items. And finally, we talked about briefly the idea of inter-rater reliability. So whenever we have non-objective tests or tests that don't automatically create a score themselves, the score has to be generated by a judge. Then we need to talk about inter-rater reliability. And there are various methods. We can look at simply the inter-rater agreement, the percentage of times that people agree versus they don't. So for example, the scores shown there, 2, 2, 2, 2, 5. You know that 75% of the time there was agreement, a 2, but 25% of the time there was vast disagreement, a 5. Also, we briefly talked about in statistics class Cohen's kappa. That basically allows us to go a little bit more fine-tune and look for the agreement, not only percent of agreement, but how likely is agreement is versus disagreement. And it, again, gives us a reliability coefficient. We can also look at interclass correlation or interclass correlation. So interclass basically means we look to see how often people are correlating on their answers. So again, if people are rating people on a 1 to 5 scale and we have a whole bunch of raters, we could run an interclass correlation and just see how often do they agree versus they disagree. Intra-class correlation, intra, means we're actually looking at the differences between different departments, for instance. So, for example, do we find inter-class correlations fairly high within groups of raters within an organization, but intra-class, intra, differences between each division in the company to be greater? So ideally, if we're looking at inter-rater reliability in a large organization that has multiple departments with multiple managers making ratings on an interview, we would want to find both high interclass and intra-class correlation. So how do we interpret these coefficients? There's no set cutoff. It depends on the use, but selection requires higher reliability than research. So again, generally speaking, we do want high reliability, and we want it fairly high if we're making decisions on it. And again, the higher the reliability, the more we can trust if it is related to a criterion or a performance measure. Generally speaking, we want to make sure the test is long enough, and the longer the test, generally the more reliable it is. We also want to make sure that we're not asking items that have a restriction of range. If the scale is on a 1 to 5, we want to make sure that at least some people would put 1, and at least some people would put 5. If everyone is responding at the top of the scale or the bottom of the scale, even though we have a 5-point scale, we might as well have a categorical scale. They either choose 1 or anything else, or they either choose 5 or anything else. So we want to make sure that we're getting those normal distributions. And again, one of the ways that we get those normal distributions is to examine the difficulty of the individual items to make sure that some of them are easy and some of them are hard, or some of the items that people would agree with most of the time, no matter where they are on that particular scale. But there's definitely some items that they would only agree with if they're very high, or they'd only agree with if they're very low. Now, once we actually have the reliability coefficient, we also want to basically create an estimate of the error, the standard error of the measurement. And again, this is based on reliability. So again, the higher the reliability, the lower the error. And we've talked about SEM in stats class as well. It's basically how much inconsistency to expect. And it's an estimate of if I have someone's test score, what is the range they're most likely to fall into. So for example, if we have an IQ of 100 and you retake that IQ test many times, how many times will you always score 100, or will you sometimes score higher or lower? So standard error of the estimate is equivalent to standard deviation of a hypothetical or hypothesis test score distribution over multiple testings. What we're really looking at is we're trying to estimate if this was the score you got from a single taking of the test, based on our knowledge of how much error is in that test, what is the range of scores that we can be pretty confident your true score falls into? So SIM is basically the standard deviation of whatever we're measuring divided by the square root of 1 minus reliability. So again, if we had a reliability of 0.9 and a standard deviation of 10 with a test score of 50, we'd basically run through the math on this one. So again, our standard deviation is 10. 1 minus reliability, 1 minus 0.9 is 0.10. We take the square root of that. So 10 times the square root of 0.10 becomes 3.16. So if the test score was 50, we now know the person's range of scores is 50 plus or minus 3.16. So the true score has about a 68% chance of falling between 46.84 and 53.16. We see the use of standard error of the measurement very commonly in selection techniques for larger companies when a large number of employees are applying for a position, because a lot of times what a company will do is instead of just setting a cutoff score of you've got to get a 50 or higher on the score on this particular test, they'll actually create a test score band based on the standard error of the measurement. So as long as you're within the error bars of the breakaway score, you would still be selected. Let's talk briefly about generalizability theory. It's a new approach to reliability and looking at multiple sources of error variance to simultaneously in a single design using an ANOVA. In a generalization study, systematically vary dimensions, facets along which error might occur. So generalizability theory is just another way to look at, you're looking for bias. So if you have a predictor, and that predictor has been found to be reliable, one of the next things you could do is how generalizable is that reliability across any bias that we're interested in. And bias that we're interested in is usually going to be driven by the EEOC. So we'd create an ANOVA test where we would actually put in most of the categorical variables that we're worried about potentially causing bias. So again, if we have a measure, let's say we have a measure of cognitive ability, we would then run an ANOVA with cognitive ability, that measure, as the outcome. It's the actual DV. And the IVs would be protected groups. We would have an IV for ethnicity or race. We'd have an IV for gender. We'd have an IV for age. We might have an IV for religious preference. And we'd ask, does this test change? Is there a significant difference in how women versus men perform on this test versus African American versus European American, those under 30 over those over 60. And if we found those differences, that would be an indication that this is not a particularly generalizable test, and it is a test that might result in creating 4/5 violations according to EEOC law. So, for example, managers write answers to 2 experience questions on 2 occasions and are rated by 3 examiners. Our facets in this case is the topics they rate, the occasions, and the examiners. And we do a decision study to see, is there a difference in the outcome scores? So this would be an example of just looking at kind of inter-rater reliability using generalizability theory. So we're not necessarily looking for group differences, we're actually looking for differences in what particular questions were rated, which occasions were done, and who did it. And again, we'd hope to find that there is not a significant difference in the ratings dependent on when the tests were done, who they were done by, or which questions were asked. So the final thing I want to talk about in this part of the lecture is basically just kind of a brief overview of what we want to do when selecting and creating tests. The first step always should be determine the measure's purpose. Why are we measuring this? What is our intent? Are we measuring this for selection purposes? Are we measuring this because it's related to a key part of the job role that's in the job analysis? Once we've determined the purpose of the measure, what are we using it for? Promotion, selection, training development. We then need to define the attribute. What is the attribute that we're measuring, and what is the evidence from the job analysis or previous study that it would be related to the outcome that we're interested in? We're then going to develop a measurement plan. So how are we going to measure it? How are we going to test it? How are we going to look at validity and reliability? What is the process? We're then going to write items or acquire items, or if we're actually just selecting a test, looking for existing tests that are out there. Once we have our test, we're going to conduct a pilot test study within our organization. And that might be a split half study, that might be a Cronbach's alpha study, it might be a test-retest study. Once we have the data, depending on the type of test, we're probably going to conduct a traditional item analysis. We're going to be basically looking for clarity, distractors, difficulties, discrimination. Is this test in general operating in such a way that it discriminates between high performers and low performers? Is there a restriction in range? Is everyone scoring very high or very low? Next, we're going to conduct an IRT analysis, hopefully, where we actually look at each individual item. Are there certain items that we should be getting rid of? And also, if it's a knowledge test, what is the chance of people guessing? Based on all of this, we're going to refine those items into the final test. We're going to select items, and then once we have the final test, we're going to actually do an additional reliability and validity test. And that is going to then, hopefully, once we find if it is reliable and valid, that's going to become a part of what we would use to defend this test if it was ever brought to court, or if we're wanting to make sure that we're just doing a good job of the prediction that we're doing. And finally, just recognize that a part of that process, we may need to revise and update that test as the role changes, as culture changes, as language changes. If you read a measure that was made in the 40s and 50s, you're probably going to see some terminology and words that are completely grammatically and English correct, but just aren't in common use anymore. So tests do change, and as they change, they may not quite measure as well as they used to.